Denis Dobkowski-Ryłko, who is my current PhD student. And he will give a talk on isolated horizons, near horizon geometries, and the Petrov type D equation.
Okay, I think it works. Okay, thank you for the introduction. So this talk will be based mainly on the 6 papers of Professor Lewandowski, Tomek Pawłowski, Adam Szereszewski, Wojtek Kamiński, Professor Racz, and Maciej Kolanowski, but also some other older work on the related topics. So first, let me start with the plan. The talk will be divided into 2 parts. The first part will be on the non-extremal isolated horizons, and the second one on the extremal ones. Okay, for the first part, I will introduce the type D equation, solve this assuming different topological structures of the horizon, namely that the section of the horizon is of an axisymmetric 2-sphere or of a genus greater than 0. But also we'll consider some non-trivial topologies of the horizons. And then we'll also consider a case with a bifurcated Petrov type D horizon that is consisting of 2 intersecting Petrov type D horizons. For the extremal case and the near horizon geometry, I'll focus on the near horizon geometry equations in n+2 dimensional spacetime, and also I'll reduce the dimensions to the regular 4 and solve this equation for genus equals 0 and for genus greater than 0. Well, maybe not in all of the cases, but assuming some additional assumptions. Okay, and finally, I'll talk about spacetimes that are foliated by non-expanding surfaces of dimension 1 that give rise to the transversal extremal horizon. Okay, so the theory of isolated horizons is the local approach to black holes. The intrinsic geometry consists of induced metric tensor and an induced covariant derivative that both have the physically relevant features of the geometry of black holes. These surfaces and the theory of these surfaces can be applied, for instance, to cosmological horizons or to null boundaries of the conformally compactified asymptotically flat spacetimes, or for instance for the bifurcated or for the black hole holograph structures of spacetimes about Killing horizons. So they also actually have some analogous properties of black holes. There are, for instance, the isolated horizons admit, for instance, mechanics that is an analog of the black hole thermodynamics. There is also the rigidity theorem, the uniqueness theorems, and actually the key difference that distinguishes these 2 approaches is that the families of solutions of stationary black holes is finite dimensional, whereas here isolated horizons, the intrinsic geometry has infinitely many degrees of freedom, and that makes it more general. And one could ask a question then, what, for instance, distinguishes the 2-dimensional family of Kerr solutions? And to answer this question, you'll have to wait for a moment. It will be discussed. So now consider a 3-dimensional null surface H that is endowed with the degenerate metric tensor GAB and the covariant derivative nabla. For the objects living on the horizon, I'll be using the lowercase Latin letters. And this surface H is, we consider it in the 4-dimensional spacetime M. Next, we assume the Einstein equations, and we call L the null and tangent vector field to the horizon. We then assume that that T is an extension of L in the neighborhood of the horizon, and that these three equations hold. So the first one is the Lie derivative of metric tensor with respect to the vector field T, and the vanishing of it is regarding in our vocabulary as a stationary to the first order. The second to the zeroth order, sorry. Yeah. The second equation, that is the commutator of the Lie derivative and the covariant derivative, is the stationarity to the first order, and then finally the last equation is the stationarity that defines basically the stationarity to the second order, and I assume that this equation they're all hold on the horizon. Okay, now we define the rotation potential omega that contracted with L gives a surface gravity kappa, and this surface gravity is constant. However, for the first part of the talk, I'll also assume that it is non-zero. Okay, now when we have the section of the horizon and the following data on it, that is the one from omega and the metric tensor GAB, from this we can actually obtain the data on the horizon, and then the full metric tensor, covariant derivative, and the Riemann tensor all on the horizon. Okay, so now the condition that we're gonna be using is the type D equation, and before I show you this condition, let me first discuss a little bit the Weyl tensor in the Newman-Penrose formalism. We know that this tensor can be expressed in terms of 5 complex-valued components. The first 4 of them are constant along the null generators of the horizon, whereas from the stationarity to the second order, we obtain the fact that the psi4 is also constant along the generators of L, null generators of L. Now, since L is expansion and shear free, it's easy to see, it's easier to show that psi0 and psi1, they both vanish, whereas psi2 can be expressed in terms of the Gaussian curvature K, capital omega, and the term with cosmological constant, where the capital omega is defined as follows, together with on the left-hand side we have the area 2 from eta, and on the right-hand side we have the exterior derivative of omega. We can also define psi, that is just this term, minus 1/2 of the times k plus I omega. Okay, now let's think of the possible Petrov types that we can have here. The Weyl tensor, the spacetime Weyl tensor is completely determined by the following data: the section S of the horizon, the metric tensor, and the one from on this section, the one from omega. L is parallel to the null. L is parallel to the double null direction, so we already can exclude the Petrov type 1 on the horizon. Now we can have Petrov type 2, Petrov type D. If we wanted to have Petrov type 3 and Petrov type N, the psi2 component would have to vanish. And if this was the case, then all other components would vanish too. So we would obtain type O. Therefore, I can exclude type N and type 3. So, as I already said, if psi2 is equal to 0, then we're dealing with a type O. And in this case, the Gaussian curvature is equal to lambda over 3, and the one from omega is closed. And for psi2 non-equal to 0, in generic case, the type of the Weyl tensor on the horizon would be 2, but there might be some equation satisfied that would suggest that it is of the type D. Okay, so we'll be using the null frame, null 2 frame on the section of the horizon with the following expression for the area 2 form. And let me conclude with the following theorem. So the Y tensor is of the Petrov type D on the horizon if and only if the following two expressions, two equations or inequality are satisfied. So first, psi2 cannot be equal to 0, and then second, this equation has to be satisfied, and this is exactly the equation to which I'm going to refer to as the Petrov type D equation. Okay, so now we'll talk about the solutions of this equation. First case is when the section of the horizon is an axisymmetric two-sphere. So I'll introduce the following metric tensor. This is a standard two-sphere metric with the conformal factor depending only on the omega, on the data, we consider the following transformation and obtain such metric where P depends only on X, which comes from the axial symmetry. We want this metric to be regular at the poles. The poles here in terms of X are just X being equal to plus minus 1. And these conditions are as follows. P has to vanish on the poles, and we also don't want to have the conical singularities, and therefore the first derivative of P squared in terms of X has to be equal to minus plus 1. In this case, the Petrov type D equation takes a simple form, and we can see that the left-hand side of this equation is the solution, the general solution, where C1 and C2 are the complex parameters or complex constants. And we can compare this result to the previously shown expression for psi2, use the regularity condition, and solve these equations. So let me state the result in the following theorem. The family of axisymmetric solutions of this equation with the cosmological constant can be parameterized by the two numbers, that is the area and angular momentum. And these numbers can take the following values depending on the cosmological constant. So for the cosmological constant greater than 0, as long as the area is smaller than 12 pi over lambda, the angular momenta can take any real values. However, for the area greater than 12 pi over lambda, we have some constraint on the angular momenta. For negative cosmological constant, we have basically no constraints as long as, obviously, area is greater than 0. A similar result has been shown by Professor Lewandowski and Tomek Pawłowski for the vanishing cosmological constant in 2003. Okay, now what about the embeddability of this solution? Well, for every solution that defines a type D isolated horizon whose intrinsic geometry coincides with the intrinsic geometry of a non-extremal Killing horizon is contained in one of the following spacetimes. It's Kerr de Sitter or anti-de Sitter spacetime, Kerr de Sitter or Schwarzschild de Sitter or anti-de Sitter, or the near horizon limit spacetime near the extremal horizon contained in either the Kerr de Sitter or Schwarzschild de Sitter spacetime. Okay, now we consider the section of the horizon to be of a genus greater than 0. And we first consider the following metric tensor with Z and Z being a complex coordinate with the following area 2 form, and M is just equal to P times D over dz. M bar is the complex conjugate of that. So now the Petrov type D equation takes the following form. It can be integrated and shown the result of its integration is the following. However, the term in the bracket is the entirely holomorphic function, and one can construct a globally defined holomorphic vector field. The dimension of space of holomorphic vector fields is known, and for the genus greater than 0, it's just 0. However, for the genus equal 1, it is a constant. But we can show that it also has to vanish in the genus equal 1 case. We just take this expression, input the term for the area 2 form, and then take the exterior derivative, extract the exterior derivative, and from the compactness it follows that this term has to be 0, therefore f has to be 0 as well. We perform some additional calculation, but quite similar to the previous ones, and show that that on the compact 2 surface of genus 1, the only solutions that we have for the Petrov type D equation are such that d omega is vanishing, so we have only the non-rotating case, and the Gaussian curvature is equal. It's a constant, but non-equal to lambda over 3, because this case would indicate the Petrov type O. Okay, now let's consider the isolated horizon that is of a non-trivial principal boundary topology. In this case, this integral is non-zero, as previously. It is equal to 2 pi times the surface gravity kappa times m, where m is an integer characterizing the U1 boundary. We introduce a new parameter n that is just equal to kappa times m, and solve this case assuming axial symmetry, assuming that S is a two-sphere, axisymmetric two-sphere. So for every value of topological charge m, the family of solutions can be parameterized by 3 parameters. One is the area, another one the surface gravity, and the third one is related to the rotation. How about the embeddability of the solution? Well, here we have 3 classes of the solution. The third class is the most generic one, and this is the class, and this is the result that we are not able to find its embeddability in the known type D solutions. The second class is special. It's for r squared being equal to 1 over 2 lambda prime. Lambda prime here is just lambda over 6. The first class, on the other hand, is quite special too. It's parameterized by r squared and n, and this class is embeddable in the tab-of-nut spacetimes. Okay, now let's consider the bifurcated Petrov type D horizon. Just like I said previously, it consists of 2 intersecting horizons that are of the Petrov type D. S is a 2 manifold on which we have the same metric tensors, right? On H prime we have one from omega that differs by a sign to the omega on the other horizon, and well, if you remember the expression for psi, one part of psi contains capital omega, and the sign of the lowercase omega also influences this sign, and therefore one psi differs from the other one by complex conjugation. So in this case, we want 2 Petrov type equations to be satisfied simultaneously on both horizons. The first one for H, that is the same equation that I've been talking about before. The second equation for H prime differs by the complex conjugation of M. If we and by this construction, we actually obtain an additional structure that becomes an axial symmetry in case of S being a two-sphere. Okay, and this setup has been considered by Cole, Raj, and Valiente Kroon, and also by Professor Lewandowski and Adam Szyszewski. Okay, so again, the same conformally flat coordinates that we've been using before. We have two equations. We can integrate them to obtain the result that's shown on the right-hand side. And next, take the partial derivative with respect to z of the first equation and another partial derivative with respect to z bar of the second one. And since the partial derivatives commute, we obtain that equation right here. And what we can do next is we can construct the vector field phi that is a priori complex in the following manner. And the result is that such vector field satisfies these two equations. And either part, the imaginary or the real part of this vector field is the Killing vector field. So now let's formulate another theorem. Let's suppose that the metric tensor and the omega and the one form omega that are defined on the section S satisfy the Petrov type D equation and its conjugate one. In such case, there exists a vector field phi on S such that these two are satisfied, and the real or imaginary part of the following term in the bracket are the Killing vector fields. And as already said, the axial symmetry here is obtained when S is the two-sphere, topological two-sphere. Okay, next topic is the next part of the talk is the extremal isolated horizons that are also stationary to the second order. So the setup is quite similar as before. Now I'll consider the n+2 dimensional spacetime with the Einstein equations. The horizon is now n+1 dimensional null surface. Again, we assume the three conditions three equations that hold on the horizon to make it to obtain the stationarity to the second order. Whereas now the contraction of omega and L will be constant but equal to 0, and this will give us the extremality condition. Now let's define the coordinate v such that on each section of S of the horizon S, v is constant, and L acting on v is equal to 1. Next, we also define the tensor SAB such that it is a second derivative of v, a second covariant derivative of v with a negative sign, and obviously S with capital letters AB is its pullback on S. Okay, so the near horizon geometries of black holes, of extremal black holes, are the exact solutions to Einstein equations and can be obtained by the naturally defined limit about the limit of the neighborhoods of extremal Killing horizons. So the first solutions were obtained when considering the extremal Reijner-Nordstrom solution and the Kerr solution. The larger family of examples can be obtained or is said by the Kunz class of solutions to Einstein equations. So here we have these two equations. The first one is the equation that all of you probably know. This is the often referred to as the near horizon geometry equation. That is equation on the omega and the metric tensor on the section of the horizon. It has been studied by many people, for instance, Hajicek in early 70s, Eisenberg, Moncrief, 83, more recently Ashtekar-Bittel and Lewandowski, but also many others. And this equation comes from Einstein equations and stationarity to the first order, whereas the second equation is quite new. It's been derived by Kolanowski, Lewandowski, and Shereshevsky in recent time. Here I drop the n for the dimensions, also exchange the covariant derivative for the semicolon, and s is just the trace of the tensor s. Okay, so first let's look at the second equation. Well, it is linear in SAB on the background of omega and metric GRB, such that the first equation is satisfied. This equation comes from the stationarity to the second order, and it is exact. However, since it's linear, it also features in linear perturbations of near horizon geometry spacetime. And this has been considered by Lucetti and Lee in 2016. Okay. Now let's consider the near horizon geometry equation and suppose that the metric tensor GAB and omega satisfy this condition, this equation. We define on the following manifold this metric tensor, and it can be shown that Einstein equations are then satisfied, and also that when setting V to 0, we obtain an extremal killing horizon that consists of, that has two killing vectors. One is V times d over dv minus u du over du, and another one is d over du. Okay, now let's focus on four-dimensional spacetime. The equation takes the following form. We assume that S is a compact two-dimensional manifold. We have a metric tensor GAB and omegas previously, but now we input K for the Gaussian curvature. Before I'll be giving you the result of, or the solutions to this equation, I want to mention some property or some features of this equation. So first of all, if we assume that this near horizon geometry equation is satisfied, it follows that the Petrov type D equation is also satisfied. However, it does not mean that the horizon is of the type D. But this type D equation becomes just an integrability condition for the near horizon geometry. Also, if S is compact, then everywhere psi2 is non-vanishing. Okay, now let's consider a non-extremal isolated horizon. So let's go back a little bit. But suppose that there is a section on which the near horizon geometry equation is satisfied. Then the null vector n that is orthogonal to the corresponding slice S is first non-expanding and shear-free, and is a double principal null direction. Okay, now suppose that S is a two-sphere. Also, we assume axisymmetry and the case where the cosmological constant is vanishing. In such case, the solution of the first and second equation is unique, modulo some rescaling where A and B are constant, and it does correspond to the horizon in the extremal Kerr spacetime. So for every solution consisting of the metric tensor, one from omega and tensor SAB, such horizon is embeddable in the extremal Kerr spacetime of the corresponding horizon area. Okay, now let's look at some topological obstacles from taking the trace of this equation and integrating over S. The left-hand side that we got here from the Gauss-Bonnet theorem, well, it depends on the genius of the considered section of the manifold. On the other side of the equation, we have one term that is positive, and additionally cosmological constant lambda. So we know that the right-hand side of this equation has to be greater than lambda, because this is non-negative. Next, let's see. Okay, so we consider first genius equal to 0. Left-hand side is just 4 pi over area, so it's positive, and therefore lambda can take positive or negative values depending on the on this term. For genius greater than 0, the left-hand side of the equation becomes negative, and therefore lambda has to be negative. So for genius greater than 1, the only solutions that we can get are those for cosmological constant smaller than 1. For genius equal to 1, either lambda is negative or it's 0, but then whenever it's 0, the 1 from omega and the Gaussian curvature have to vanish. Okay, so to conclude already, we have the axial symmetry and cosmological constant equal to 0 case, and here we obtain the extremal Kerr metric and 1 from omega. It can be generalized to the Einstein-Maxwell case, and there are no more solutions. There have been some generalization to Einstein-Young-Mills case, and also to the non-vanishing cosmological constant by Kunduri and Lucetti. So how about no axial symmetry? Well, we don't have the final result, only partially. We know that if this horizon is non-rotating, therefore if this equation is satisfied, then the only solution is such that k is equal to lambda, only for the positive cosmological constant, and the 1 from omega is vanishing. And the linearist equation about the axisymmetric solution admits only axisymmetric solutions, and this is partially a numeric result by Hrushchev, Szybka, and Todd. Okay, so the next considered case is genius greater than 0. Here, the only possible result is also k equal to lambda. However, this time lambda cannot be greater than 0, and omega is vanishing. So it's also a non-rotating case. It is embeddable in the extremal case of this metric, where these minuses are not mistakes. This is really minus, and when you take the extremal case, lambda equal to -1 over 9m squared, it gives you a spacetime that you can embed your solution. Okay, finally, if we consider a spacetime foliated by non-expanding non-expanding surfaces of codimension 1, we let this coordinate u be constant to define the foliation. We choose L to be of the following form. On each space-like section of this non-expanding horizon foliation, we have the condition that looks kind of like a near horizon geometry equation. However, it's dual, and for each leaf of the foliation, defines an abstract extremal isolated horizon by taking omega to negative omega, and this then becomes an the near horizon geometry equation. So this gives rise to the extremal horizon that is tangent to the transversal to the non-expanding horizon foliation. For v equals 0, we get this extremal transversal horizon. And the result can be stated in the following theorem. Suppose we have the 4-dimensional spacetime M with a metric tensor G mu nu. and it is foliated by a non-expanding horizons and emanating from a single transversal isolated horizon, then the vacuum Einstein equations with a cosmological constant are satisfied only if we have the near horizon geometry spacetime that is of the following form, and the dual to the near horizon geometry equation is satisfied. Okay, so I'm running out of time, so let me just leave the summary on the board. Yeah. Okay, so what we did, we first introduced the Petrov type D equation that, when satisfied, gives us the horizon of the Petrov type D. We showed that non-twisting of the second double principal vector happens whenever the near horizon geometry equation is satisfied on the section of the horizon. Next, for all of the axisymmetric solutions of the Petrov type D, well, they can be, in general, in a section of the two-sphere, they can be parameterized by two parameters, but when we assume that the horizon is of the non-trivial principal fiber bundle, then we got three parameters that parameterize this family of solutions. All of the solutions were found also for genus greater than 0. They were non-rotating. For the problem of existence of non-axisymmetric solutions on topological sphere, well, this is still not solved, so it remains an open task to do. Then I talked about the bifurcated horizons and the fact that we can obtain the axial symmetry without the rigidity theorem. And last, we talked about the near horizon geometry and its solutions for genus equal to 0 and genus greater than 0. And that's it. Thank you.
Questions or comments? So you didn't mention that we have this problem with embeddability of horizons which are hop bundles.
Yeah, I mentioned that we didn't find the embeddability, but I didn't discuss it in detail. But yeah, we were thinking that maybe. Okay, let me go back. Okay, here. So this generic solution on the non-trivial bundle topology of the horizon. Well, this is we haven't found the embeddability for this solution. We're thinking that possibly it could be embeddable in the Kerr knot spacetime. However, it is not possible since we assume the regularity condition on the poles of the horizon, whereas in the Kerr knot spacetime there are singularities. You can get rid of one singularity at one pole, but then you're still left with another on the other pole. And we're trying to find it also in the general Plebański-Demiański spacetimes, but so far with no luck, and it seems like they're not embeddable in this spacetime.
I think they are embeddable.
Well, with regularity conditions, I mean.
Yeah. I think there exist such spacetimes. They're just not explicitly distinguished in books. So they're hidden somewhere in the existing. Okay, if there are no more questions, it's time for coffee break. So let us think.